In this video, we will go over the last topic of this unit, which is quadratic equation word problems. Now, we did word problems earlier in the unit, but they were max-min word problems. Now, these word problems are basically they involve quadratic equations which you have to solve. Okay, so we've been doing a lot of solving in the past few lessons. We can solve by factoring, we can solve by using the quadratic formula, and if you forget the quadratic formula, you can solve by completing the square. But you know what? At the end of the day, we just need to be able to solve a quadratic equation to answer these word problems. Now, there's actually one more hurdle we are going to face with these word problems. Because we have to generate the quadratic equation. It's not going to be given to us. This is very reminiscent of what you did in the first unit with linear systems. Now, in the first unit, it's very easy or straightforward if we just give you the linear system, and then you can solve by substitution or elimination. But it gets harder when you do the word problems because you don't have the system. You have to generate the system. So really, there are two parts to this question. You have to generate the equation and then solve the equation. Generating the equation is the hard part because that requires you to interpret the word problem, whereas the part that's pretty formulaic. Okay, it's you've done hundreds of questions by now, hopefully, and you can do it in your sleep. You know what? Without any further ado, let's solve a few of these quadratic equation word problems. The length of a rectangle is 3 centimeters more than the width. The area of the square. The area of this rectangle is 108 square centimeters. Find the length of the rectangle. Okay. Let's draw our rectangle here. Okay. The length of a rectangle is 3 centimeters more than the width. The length of a rectangle is 3 centimeters more than the width. So if this is the width of the rectangle, then the length will be W plus 3, because they told us that the length of the rectangle is 3 centimeters more than the width. Okay, so width, 3 more than the width. Now, there's nothing wrong with what I drew, but I just want you to understand, because the question is asking for the length of the rectangle, this diagram, or what I've written here, won't solve for the length of the rectangle. It will solve for the width of the rectangle. So there's just an extra step, which is perfectly fine. But if you want to avoid that extra step, you want to express the dimensions in terms of the length. So you would put L here and then L minus 3. Anyways, I'm perfectly happy with this. So now we have a fact that we have to use, which is the area. The area is 108 square centimeters. So W times W plus 3, because it's a rectangle. Length times width is 108. What do I see here? Quadratic equation. Okay, from here it's just really straightforward. Just, expand, set equal to 0. Okay, simple trinomial. Are there two numbers that multiply to negative 108 and add to 3? Now, if you don't know the two numbers, or you suspect that those two numbers don't exist, what you can do is use the quadratic formula. Okay. Now, if you are not sure whether it's factorable or not, what you can do is also find the discriminant and see if it's a perfect square. But let me just quickly check. I do suspect it is factorable. I'm just checking the numbers here. Oh, yes. Well, that was, I didn't need to try this. I don't know what I was thinking. Alright, of course, 12 and 9. 12 and negative 9. That was very silly. Why did it take me so long? Okay, so the solutions, now you apply the zero product property. The solutions to this equation is either with this negative, or W equals negative 12, or W equals 9. Now I forgot, we made an equation here. Let's do a let statement here, right? Just like in the first unit, let W represent width of rectangle and we're going to say that it's in centimeters. So this makes no sense. How can So we're going to say inadmissible or reject, and then you say because the width has to be greater than 0. I can't have a dimension which is 0 or negative. Makes no sense. So if that's the case, reject that. So we have one great solution. But if you read the question, like I said earlier, it says find the length of the rectangle. So the length is 3 more than the width, right? That's the first sentence. It's 3 centimeters more than the width, so it's going to be 9 plus 3, which is 12. Therefore, the length is 12 centimeters. Okay, so once again, there are really two parts. Build the equation, solve the equation. Building the equation is the hard part. So two cars leave an intersection. One car travels north, the other travels east. When the car traveling north had gone 24 kilometers, the distance between the cars was 4 kilometers more than 3 times the distance traveled by the car heading east. Find the distance between the cars at that time. Okay, so let's start off by drawing a diagram here. So I have one car going north and one car going east. So it works out beautifully. Okay, the car going north had gone 24 kilometers. Okay, beautiful. Now, they tell us that one car is going east. Now, we don't really know that distance. So, I'm going to let x represent that distance of the car heading east. Now, then they also say that the distance between the cars was 4 kilometers more than 3 times the distance traveled by the car heading east. So, this is going 3x plus 4, right? 3 times the distance traveled by the car heading east. So 4 more kilometers than 3 times the distance traveled by the car heading east. So it's 3x plus 4. So before I forget, let's do a let statement. Let x represent distance traveled by car heading east. Okay. So now if you look at this let statement, it's not the best let statement because the question is not asking you how far the car traveled east. What's the distance covered by the car traveling east? That's not the question. The question is how far are the two cars apart? So if you solve for x, that will not directly answer the question. You have to do an extra step, just like what you did in question 1, which is not a problem. The most important part is really to build the correct equation. So, how can I build this quadratic equation? There's a tool that's going to help us out. Yes, right triangle, Pythagorean theorem. So x squared plus 24 squared equals 3x plus 4 all squared. Bam, there you go. That's the quadratic equation. Time to solve this. 576, 9x squared, 12, 24x plus 16. Set equals 0 because you want to apply your zero product property. Divide both sides by 8. And then what multiplies to negative 70 and adds to 3, 10 and negative, oh my gosh, 10 and negative 7. So now I apply my zero product property, x equals negative 10 or x equals 7. But wait a minute, negative 10, we reject that. Reject that because x is greater than 0. The car traveling east, he must have traveled east. He must have traveled because the car going north has already gone 24 kilometers. So the car going east must have traveled some distance, okay? And no matter how slow he's going, he has to go somewhere, okay? So it has to be greater than 0. Negative 10 just makes no sense. In fact, I know that he's traveled 7 kilometers. Now, if he's gone 7 kilometers, the car going east, what's the distance between the cars? Well, I have an expression here that's going to help me. Distance between cars is triple of 7 and add 4, which is 25. So therefore, the distance between the two cars at that time is 25 kilometers. There we go. For example 3, we have a classic test question. An area rug has a central 5 meter by 3 meter rectangle in a mosaic pattern, and with a plain border of uniform width around it. So let me try to draw a nice little rug here. Okay, you have a mosaic pattern that's 5 meters by 3 meters. Okay, and what we are going to do is we're going to add a border around this. Okay, and of course, to make it look pretty, it's a uniform border. So this is X, this is X, this is X. Okay, it's a uniform border. That makes sense. Most borders I've seen in my life are uniform width. Okay, so if this, let's start with this. If this is X, this is 5 meters, and this is X, then guess what? This is 2x plus 5, right? And if this is X, this is 3, and this is X, then this is 2x plus 3. All right. Now, like I said, really the hardest part to the question is build an equation. Now, before I build the equation, let's do a let statement. Let X represent width of border. And this is in meters, of course. So now I think we're ready to build the equation, because there's one little fact we have yet to use, which is the total area of the rug. So it's 2x plus 3 times 2x plus 5 is 24. So solve that quadratic equation, no problem. 4x squared, this is 10 plus 6 is 16x plus 15, set equal to 0. I'm getting ready to apply the zero product property. Alright, let's see if this is factorable. Complex trinomial, no problem. 9, ooh yeah, 9 and 1, because this will make 18, this will make 2. Plus 18 minus 2. So, students struggle with extracting the roots from when the factors look like this, so I'll show all my steps. So 2x minus 1 equals 0, or 2x plus 9 equals 0, based on the zero product property. So from this, I get x equals half. From here, x equals negative 9 over 2. Wait a minute. Negative 9 over 2, reject that. Now, sometimes a negative solution is perfectly fine, but the negative 2 in this case makes no sense, because x has to be greater than 0. Because the original area is 5 by 3, and the total area is 24. I know that the width of the border can't be 0 or less than 0. Because like I just said, this is 15 and the total area is 24. I have to add something. I have to add a width so I can increase the area from 15 meters squared to 24 square meters. Anyway, so x has to be greater than 0, reject that. So the answer is half actually. So therefore, the width of the border is half a meter. So for example 4, we're told that a company models its annual profits using the function p equals x squared plus 20x minus 300. P is profit in thousands, x is the number of units sold. One year, their profits were $176,000. How many units of their products did they sell? Before we answer this question, I want to tell you that I feel that this question is on the easier side, especially when you compare it to question 1, 2, and 3, because you don't have to generate the equation. The equation's already given to you, okay? All you have to do is quite simply let p equal a number. Now, a very common mistake that students make is that they let p equal 176,000. But be careful, p already entered in thousands. So if the profits were to be 176,000, you should just let p equal 176, not 176,000. Okay, huge difference. So anyways, once you let p equal 176, which is pretty straightforward, you have your quadratic equation, right? You don't have to draw a diagram, you don't have to think really hard, you don't have to use the Pythagorean theorem, you don't have to think about the area, just let p equal 176. So now I see a quadratic equation, and I'm going to solve this. I see a simple trinomial. Is this factorable? If you don't know whether it's factorable or not, or you can't factor it because you don't know two numbers that multiply to 476, a negative 476 and add to 20, then you know what? Just take out the quadratic formula. I'm a little stubborn. I think it is factorable, so I'm just going to quickly run through the numbers. Oh yeah, 34 and negative 14. 34 times negative 14 is negative 476, and if you add those two, they give you 20. So perfect. So now apply the zero product property. So from the first factor, x plus 34, x is equal to negative 34, or x is equal to 14. Well, this makes no sense. I can't sell negative units of products. So reject, because you can sell nothing, I guess, but you can't sell less than nothing. It makes no sense. Okay, so you can sell 14 units. Therefore, they sold 14 units of their product. All right, so let's try example 5 here. An open top box is made by cutting 3 centimeter squares from each corner of a square piece of cardboard and then folding up the flaps. The volume of the box is to be 1083 cubic centimeters. Find the dimensions of the original piece of cardboard. Interesting. Okay, so you know what? This one is a little harder to visualize for students. I'm going to hopefully draw something nice for you. Okay, so you have a square piece of cardboard. Okay. You know what? I find that confusing, so this is X. Okay, so you have a square piece of cardboard. Okay, it's measuring X centimeters by X centimeters, and what you're going to do is you're going to cut squares from the corner. Well, now, why would you do such a silly thing? Because if you cut the squares, you basically have a cross, right? A weird looking cross, but a cross nonetheless. And if you fold up these flaps, then you can make your open top box. Okay, so what's important to note is that the squares you're cutting out they're 3 centimeter squares. So this is 3 centimeters. Okay. Let's add that here and here. You know what? Let's try that one more time. 3 centimeters. Okay. So just to highlight, it has nothing to do with whole dimension. It's just the square. Now, what about from here to here? Okay, if this is 3, this is 3, and the whole thing is x, then hopefully you can imagine that this is 3 minus 2x. Oops, oh, that's horrible. That's not 3 minus 2x. It's x minus 6, right? 3 here, so x minus 6. So you know what? I'm going to redeem myself by drawing a really pretty picture. Oh, the pressure is on now. The pressure is on now. You know what? That's from by my standards. I'm gonna live with that. So, okay, let's see. Hopefully you know that the dimensions of the base of this box is x minus 6 and x minus 6. Okay, because this is x minus 6, because it's a square, right? And you cut 6 basically 6 centimeters off the x. So yeah, x minus 6, x minus 6. And what about the height though? What about the height of this box? Well, the height, believe it or not, is actually just 3, because the flap is 3 centimeters. Yeah, this dimension is 3 centimeters, so when you fold it up, it becomes 3 centimeters high. So there you go. Ooh, okay. Now before we build the equation, we should really do a quick let statement. So let x represent length of a side of the square cardboard. And of course, it's measured in centimeters. Okay, so if we solve for x, we know the length of one side, and then we can answer the question. Because the question is asking me the dimensions of the original piece of cardboard, which we know is the square. So if we know one of the sides, then we can tell the dimension of the square. Okay, so we got to build the equation. So that's the hard part to the question. There's one piece of information we have yet to use, which is the volume of this box. So x minus 6 squared times 3 is 1083. Okay, divide both sides by 3. 1083 divided by 3 is 361. Expand that, perfect square trinomial. Set equal to 0. Alright, negative 325. And then we ask ourselves, is that factorable? Please cross your fingers. Let's check. Yes, it is. So it is 25 and 13. 25 times 13 is 325. But you want negative 325, so it's negative 25 plus 13. Zero product property, so x is equals 25, or x is equal to negative 13. But wait a second, if x represents the length of a side, then you know what? Reject, because x has to be greater than 0. I have to have a dimension which is positive. I can't have a 0 or negative dimension. Therefore, the original cardboard has dimensions of 25 centimeters by 25 centimeters. Okay. Last one. The sum of the squares of two consecutive positive integers is 85. What are the integers? So this question I added because it's like what you did in grade 9. So what you did in grade 9 was the sum of two consecutive positive integers. But now, since you can solve quadratic equations, not just linear equations, you can turn it up a little. Sum of the squares. So two consecutive positive integers. So I'm going to say x squared, and then the second integer will be x plus 2, right? Oh, sorry, not consecutive even, consecutive positive. So x plus 1. Okay, they're consecutive positive integers. You could do x and x minus 1 is 85. Okay, let's do a quick let x represent first of two consecutive positive integers. Okay, that was the hard part, building the quadratic equation. Now it's time to solve. Okay, 2x minus 84. Divide both sides by 2. It's an equation. So let's say 42. Ooh, factorable. Sometimes you do have to use a quadratic formula. But luckily we didn't have to do it for these examples. But you know what? You're always welcome to use a quadratic formula if you can't factor. zero product property, reject. Why do I reject? Because they said positive integers. So x, because x we're told is greater than 0. Therefore, the two integers, or let's say the two positive integers are 6 and 7. Let's quickly check what's 6 squared and what's 7 squared. 6 squared and 7 squared. Oh yes, 85. Perfect. Feeling good. Okay, so that was the last lesson. We can now solve quadratic equations, the word problems involved with solving quadratic equations. Now, like I said, the hardest part is really building an equation. We've really mastered the skill of solving a quadratic equation itself. The hard part is really just building it and interpreting the word problem. But with practice, it gets easier. So with all that being said, let's take up the homework in the next video.